Let's wrap up sections 1.2 and 1.3. Because the Martian alphabet data had a 50% chance of correctly identifying Bumba if we were randomly guessing, we could use a coin to model the outcome from one trial, or for one student. But that won't work for water tasting. What could we use instead? Well, there are 4 cups from people to choose from, so the chance of choosing tap water randomly should be 25%. So we need something that can be broken down into a 25% chance of occurring. A 4-sided die would work, but a spinner would be even easier. Here, you see a spinner with 4 options. Not that technically we need all 4. All we really care about is whether they choose tap water or not. So we could make the variable binary, meaning 2 options, where tap water has a 25% chance of occurring, and not tap water has a 75% chance of occurring. Back to the 3S strategy. Our statistic is p hat equals 3 out of 27 for the water tasting example. The simulation involves spinning a spinner in the applet 27 times, where the spinner had a 25% probability of success. We repeated that process at least 1,000 times to create the null distributions seen here. How do we assess strength of evidence? In 1.1, we just found where our observed statistic fell. The statistic, remember, was p hat equals 3 out of 27, or 0.111. Does that seem like it's unusual, or in the tail of the null distribution? It is pretty far in the tail, but now we know we can actually calculate how far it is in the tail by finding the proportion of simulations at least that far in the tail, determined by the alternative hypothesis, by plugging our statistic of 0.111 into the text box. In my simulation, the p-value was found to be 0.069. Yours might have been slightly different. Why? Because the simulations are random, so your 1,000 simulations, while having a similar shape, will not be exactly the same as mine. The p-value is an extremely important word in this class. You really need to understand what it means and how to interpret it. The p-value is defined in your textbook as the proportion of simulated statistics in the null distribution that are at least as extreme in the direction of the alternative hypothesis as the value of the statistic actually observed in the research study. For the water tasting example, you should have gotten something close to 0.069 as the proportion of samples, or your p-value. But, of course, in this class, obtaining that value is a lot less important than understanding what it means or being able to interpret it in the context of the problem. Any p-value interpretation requires 4 components. You need to note that the p-value is a proportion of samples, or a probability, or a chance, or the likelihood of something going on. The p-value assumes the null hypothesis is true, because it was found by finding a proportion of simulated statistics in the null distribution, or statistics that were simulated assuming the null hypothesis is true. The p-value was found using your observed statistic, so that needs to be included in the interpretation, as well as the direction that we went from the observed statistic, which will always be the direction of the alternative hypothesis. Let's look at 2 examples. Let's do some examples of interpreting p-values. First, using the Martian alphabet data. Let's use a class of 40 students where 35 correctly identified Bumba, so p hat is 35 out of 40. If you'd analyze this data, you would get a p-value of less than 0.001. We would interpret that by saying, if students are randomly selecting between the 2 symbols, for which one is called Bumba, or if the null is true, then in less than 1 out of every 1,000 samples of 40 students, we would see 35 or more correctly identify Bumba. 35 out of 40 is our statistic, or more is the direction, and our probability or proportion of samples is less than 1 out of every 1,000. In the water tasting example, you should have gotten a p-value of around 0.069. In other words, there is a 6.9% chance or probability of seeing 3 or fewer direction people choose tap water in a sample of 27, 3 out of 27 is the statistic, if 25% of all people would choose tap water, if the null is true. The following information is on pages 39 and 43 of your textbook and helps us to assess the strength of evidence based on the p-value. Copy this into your notes and highlight it. It is extremely important. Note we are always assessing strength of evidence against the null hypothesis. Also note the lower the p-value, the stronger the evidence against the null. Why? Remember, the p-value is the proportion of simulations under the null distribution at or beyond the observed statistic. If the p-value is low, that means there are very few simulations more extreme than what we observed in our sample, so our statistic is in the far tail of the distribution, and therefore the chance model is not a good explanation for our data. Based on that p-value of 0.069, it would fall into the moderate strength of evidence, so we would say we have moderate evidence that the proportion of people choosing tap water among 4 options is less than 25%. Note that this conclusion is written in terms of the alternative hypothesis, less than 25%. That should always be the case. P-value provides evidence against the null, but tell us about the alternative. Let's review. On this null distribution for the water tasting example, what does a single dot represent? That would represent one set of 27 people picking a cup at random from 4 possible cups. Note that we have to include the assumption of random chance when describing one dot on a null distribution. So what would we say the whole distribution represents? It represents a plot of proportions that picked water from 100 different samples of 27 people who picked a cup at random from 4 possible cups. The p-value from this distribution was 0.07. And what does that p-value mean? In 7 of 100 samples of 27 people who picked a cup at random from 4 different cups, 3 or fewer people chose tap water. So far, we have assessed strength of evidence either by simply comparing the observed data to the null distribution or by having the applet calculate a p-value. There is a third way, one we can calculate by hand, called the standardized statistic. For a single proportion, we will use the symbol z for standardized statistic. The z-value is calculated by finding the observed statistic minus the hypothesized mean of the null distribution, and then dividing that quantity by the standard deviation of the null distribution. The standardized statistic gives the number of standard deviations our sample statistic is above the mean of the null distribution, or below if the standardized statistic is negative. Note in the formula above, we use the long-term proportion or probability given in the null hypothesis for the hypothesized mean of the null distribution. To find the standard deviation of the null distribution, check the box for summary stats in the upper left-hand corner of the distribution in our applet. Let's use our last 2 examples to get some practice. In water tasting, the observed statistic was 3 out of 27, or 0.111. The null value was 0.25, and according to the null distribution for these data seen at left, the standard deviation was 0.084. This gives a standardized statistic of negative 1.655. In the Bob and Tim exploration, let's pretend we use a class with 18 out of 25, selecting Tim as the face on the left. Then, the observed statistic is 18 out of 25, or 0.72. The null value in this case was 0.5, and according to the null distribution for these data, seen at right, the standard deviation is 0.10. This gives a standardized statistic of 2.2. Again, let's interpret these values. In water tasting, our observed statistic was 1.655 standard deviations below the null value of 0.25. In the Bob and Tim example, our observed statistic was 2.200 standard deviations above the null value of 0.5. We have stronger evidence against the null in the Bob and Tim exploration because the standardized statistic is farther from 0. The table seen here is on pages 49 and 52 of your textbook and helps us to assess the strength of evidence based on the standardized statistic. Copy this into your notes and highlight it. Again, it is extremely important. Note we are still assessing strength of evidence against the null hypothesis. Also note, the farther the standardized statistic is from 0, the stronger the evidence against the null. Why? The farther the standardized statistic is from 0, the more different the observed statistic and null value are in terms of standard deviations. So large standardized statistics indicate the observed statistic is far in the tail of the null distribution.